Our next speaker is Clement Campo, and his presentation. Yeah, Clement, hello. I can see you here. Very good. Clement was a PhD student for the French-German Research Institute of Saint-Louis and the XLIM laboratory of Poitiers, and he worked on developing an antenna weighting system based on commercial SDR, focusing on SDR, antenna array steering techniques, and DOA estimation algorithms. And yeah, well, in our program we have a couple of other people who also helped Clement, which is Loïc Bernard and Hervé, who we have seen before, Sebastian Anguille, and Jean-Marie Payot from Poitiers University Institute of Technology. So, the title of Clement's contribution will be Transmitting Phase-Aligned Signals for Array Steering with USRPs X310. Clement, we're going to play a pre-recorded video for the video team. Please go ahead.
Hello everyone, my name is Clément Campo. My presentation is about some work my colleagues and I carried out, and is called Transmitting Phase-Aligned Signals for Array Steering with USRPs X310. During this presentation, I will first try to frame the problem with respect to the rest of our work. Then I will present the solution we came up with to answer that problem. And finally, I will show some of the experimental results we got before I quickly conclude. Let's start by the introduction. I'm part of the STC research group, which stands for Sensors, Telemetry and Communication. Among other things, we embed electronics inside gun-fired projectiles and ensure proper telemetry reception of the embedded sensor data. Hence, we use antenna arrays on a regular basis. So, in case somebody is not familiar with this concept, an antenna array is a set of antennas that are used to transmit or receive the same signals. Thanks to constructive and destructive interferences, the radiation pattern of the global antenna is more directive than that of the constitutive ones. Here, for example, you can see an antenna array made up of 7 elements that are represented by these black dots. And we show also interference figures. Constructive interference creates a lobe, while destructive interference almost completely cancels radiation in other direction in space. And antenna arrays also allow to dynamically change the resulting radiation pattern by modifying the phase shift applied between each antenna signal. Here, by imposing -30 or +30 degree phase shift, the main lobe of the array can be steered towards minus or +10 degrees, respectively. This work was a part of my PhD called Development of an Array Steering System Based on Software-Defined Radio. I had 2 USRPs X310s equipped with 2 UBX 160 each, and I was to investigate the capabilities and limits of this setup with regards to array steering. Because of this context, the philosophy was to go as far as possible with the available commercial equipment and limit additional hardware to a minimum. To give you an example, one of the cool things we did with these USRPs was to use a 4-element array such as this one. Here you can see its corresponding PowerPoint shape. Put it on perpendicular to a projectile flat trajectory, and we were actually able to electronically follow the transmitter that was embedded in the projectile while it was flying at Mach 1. Okay. During this PhD, the main problem we encountered was that phase shifts between USRP channel signals were introduced by the conversion chains, preventing proper phase alignment. Indeed, that is illustrated here. You can see represented an antenna array steered by USRPs, which are represented by their conversion chains here. And the array is used as a receiver, so the received signals are digitized and can be visualized in GNU Radio. A reference transmitter is placed perpendicular to the array so that the planar wavefront that is received doesn't induce any phase shift between array elements. So in that case, theory tells us that we should observe phase-aligned signals on GNU Radio. But as mentioned, these conversion chains introduce additional phase shifts, and in practice, the observed signals are phase shifted. So obviously, that's going to hinder the equipment capacity to properly steer antenna arrays. And things only get worse. At this point, we thought that part of the phase shifts were induced by the SDR PLLs. So we tried to repeatedly measure the phase shifts between the channels. That's what's shown here. The first channel is used as a phase reference, and the three curves you can see here are plots of the phases of the three other channels. And not so surprisingly, we can observe that these phase shifts are nowhere close to zero, and that they do not remain constant if we repeat the same measurement over and over again. So there is some part of this phase shift that is random, and we are going to need to automate some phase calibration process if we want to properly steer antenna arrays with these USRPs. In order to address this issue in case of a receiving array, we accepted the constraints of placing the transmitter aligned with the array before measurement. In this case, no phase shift is induced by the transmitter position, so the phase shifts that are observed between the digitized signals correspond then only to the phase shifts that we are trying to suppress. So we can simply measure them and compensate for them in software. This way, we could code a software-only phase calibration algorithm that enabled the commercial USRPs to properly steer antenna arrays after this calibration was performed. We then remeasured the phase shifts between our signals before and after this automated phase calibration was performed in software. And we did these measurements over the full frequency range of the UBX160. It can be noted that prior to any calibration, these phase shifts only tend to increase with the working frequency, while after the calibration is performed, they are significantly reduced over the full frequency range. So that's what allowed us to properly steer antenna arrays in receiving mode using the USRPs. The problem that's going to interest us today is that in the case of a transmitting array, however, the phase shifts are added to the signals in the analog domain, and therefore they cannot easily be visualized in software. Since no information is available for us in GNU Radio, that means that this commercial setup without any additional hardware is not suitable for array steering. That brings us to the second part of the presentation. It is the solution that we propose to address this issue. We stated that we wouldn't be able to achieve phase alignment without any additional hardware, so that's what we did. The idea here is to loop a portion of the transmitted signal using passive RF components placed between the USRPs and the transmitting array, and build on the previous results to measure and compensate for the phase shifts in software. The principle is represented here. We have available in GNU Radio the digital baseband signal carrying the information we want to transmit. This signal will be converted to the RF analog domain and will suffer from the phase shift associated with the transmitting conversion chain. So part of the signal is going to be looped thanks to the calibration circuit, and we will not here write the terms due to the passive RF components, as they are deterministic, can be measured beforehand, and are just going to make the equations harder to read. Finally, these looped signals, we go back to the digital baseband again, and that's going to make us available an image of the baseband original signal and the phase shift induced by the conversion chains. So what we're going to try to do here is to isolate this term that we want to compensate. And to do that, we are going to need, as a mandatory first step, to remove that term from the equation. Here is shown a picture of the actual calibration circuit. We have, in practice, access to the 4 available transmitting channels of our 2 USRPs, and you can note that we are only going to use 2 reception ports to loop our signals. Here is shown the associated figure. Any number of USRPs can be represented by the transmission conversion chains, but independently from that number, only 2 conversion chains are used for the reception. During the first step, the signal transmitted on the first channel, which is chosen as a phase reference, is looped back to both receiving channels using a power splitter. This way, the 2 images of the signal which is transmitted on the first channel only differ by the phase shift induced by the conversion chain in reception. And by computing the fraction shown here, we can then remove this term from the next equations. Once this is done, and while the first receiving channel only allows us to visualize an image of the signal transmitting on the first transmitting channel, used as a reference, the second reception conversion chains is used to loop any of the remaining transmitted signals. Now, if we compare the expressions of the looped signals, they now differ by 2 terms. But thanks to the information we retrieved from step 1, we are now able to isolate only the terms induced by the transmitting conversion chains and compute them so that we can finally compensate for them in software. Finally, we can update the digital baseband signal to be transmitted with the term we just computed. This way, when the updated signal is converted to the RF analog domain, its new expression will look like this. And we can note that now the phase term is independent from the index I of the transmitting channel. And this should mean that the RF signals will be phase aligned when reaching the antenna array, finally enabling proper array steering. Okay, let's see some of the experimental results we got. All the presented tests used the 4 available channels of our 2 USRP X310s, so only 4 antenna elements. However, we used 2 antenna arrays, a 4-element linear array designed for a 2.3 GHz working frequency, and a 4x4 planar array used at a 3.1 GHz working frequency. The latter we used as a linear array, as shown by the blue rectangle, so that we could compare the results with the ULA, and as a 2x2 planar array, as shown in red. This way, we were able to steer arrays of different geometries and at different working frequencies with the same commercial SDR equipment. So this is the flow graph we implemented in GNU Radio for our tests. The USRP blocks give us access to the receiving and transmitting channels respectively. This block represents the signal that we wish to transmit, while this one includes the algorithms that I just presented. On a user trigger, the block will compute automatically the phase shift between the looped signals. It will also keep track of which transmitting channel is being visualized here at all times, and when all the terms are computed, it will automatically apply the needed phase shift to the signal to be transmitted. And this means that the outputs of this block will represent RF analog signals when converted that will be phase aligned when they reach the array. And completely independently from what we have presented so far, we can also apply to our calibrated signals in the software an array steering algorithm of our choice. In this way, we can make the array do whatever we need it to. And for our tests, we used a beam steering algorithm in order to steer the array main lobe in the direction set by the user, just as in the animation we saw in the introduction. The first result plots the radiation patterns measured with the transmitting ULA at 2.3 GHz. Each colored plot corresponds to a given direction θ set by the user for the array main lobe. The measurement shows that for values of θ between -30 and +30 degrees, the main lobe is effectively centered around the value of θ set by the user. That is to say, that the lobe is steered correctly. The second measurement uses a row of the planar array as a ULA centered at 3.1 GHz. And once again, the lobe is correctly steered towards the direction set by the user. So far, hence, results demonstrate that the two arrays can be steered at different carrier frequencies with the same hardware. The last two measurements use the 2x2 planar array configuration. Radiation patterns are measured in two orthogonal planes to assess the system capability to steer the array lobe in two dimensions, and this one is referred to as phi equals 90 degrees. The main lobe is bigger here than for the ULAs, which is normal since we only use two elements per dimensions, but nevertheless the main lobe can still be steered towards the direction set by the user, as in the previous measurements. At last, we look at the same measurement, this time in the plane phi equals 0 degree. As lobes can be steered in both perpendicular planes, measurements then demonstrate that this setup and algorithms successfully allow two-dimensional beam steering. And this leads us to the conclusion. So, the work in this presentation is part of an investigation on the capabilities and limitations of the commercial USRP X310s and the UBX160 daughter boards with regard to phase-aligned applications and especially antenna array steering. The case of a receiving array was investigated in a previous study and led us to conclude the commercial setup alone was enough if the condition of knowing the transmitter location before measurement could be met. However, the proposed software calibration procedure used for a receiving array does not enable array steering for transmission, which highlights another limitation of the setup. In order to address this issue, an additional calibration circuit made up of passive RF components was added, and a calibration algorithm was implemented in GNU Radio as a state machine. And with this new setup, we carried out measurements in an anechoic environment using two different arrays and demonstrated its ability to steer the array main lobes for different geometries and carrier frequencies with a single hardware architecture. This ends up my presentation. Thank you all for your kind attention, and if you have questions, I will do my best to answer them. Thank you.
Very interesting talk, and well, it seems we have a topic here in this block, which is concurrent signals, multiple antennas, multiple receivers, and how to calculate these signals. That's a very interesting topic in general, which is my introduction now to panel number 2. Well, this was kind of a panel just before, but we needed to bridge some time. But I would like to raise this topic now for this panel, for these 15 minutes which we have, whether or not, or how you see it, is radio becoming a quasi optical discipline? Because we've just seen a real two-dimensional antenna array, which allows to create multiple beams, which allows to create multiple receiver sensitivities in different directions. And in fact, I see lots of applications, particularly in the car industry, for autonomously driving cars, detecting people and all sorts of obstacles on the path, and creating picture-like impressions of what's going on out there on the street. I also remember a little conversation which I had a couple of years ago on an electronics trade fair here in Munich, where a representative of a company said, for example, in construction sites, of course you can have laser detectors or detectors of instruments and devices moving around on the construction sites, but they prefer radar because, particularly if it's a dirty environment, dusty environment, when optical sensors are possibly covered by dust and by dirt, they just fail. They can't give you any more picture. But a radar sensor is inherently independent and cannot be blocked by dust and dirt. So are we seeing the emergence of radio frequency as a quasi-optical discipline, and what are the effects you could figure out? So this is my question from an application perspective. And the second question there would be, okay, we've seen just a few signals that are calculated against each other. What is your estimation of scaling this to a massive scale? For example, if you don't have just a 4x4 array, but let's say a 100 by 100 array, is that thinkable in the near future?
Thank you, Marcus. About your first question, I don't know if I am the person to answer about are we really seeing the emergence of SDR architectures as able to provide new systems and really bring the RF frequencies to the quasi-optical link applications. I can tell you that in ISL we are currently trying to see if we can start projects in which we would try to effectively use SDRs as systems that would work as radars for different applications. So I think that now this technology might be able to provide to enable these kinds of systems. But once again, that's up for debate. We are now only in the beginning, and as always, there will be issues that, as for now, I'm not able to answer. I don't know if you had any particular example in mind at that time. You mentioned civil applications. That's not really the one I'm focused on at the moment. But yeah, that's definitely a debate that I would like to go further in. Um, I will try to answer your second question. So you asked me if thinking of this system as it's, let's say, a basic brick for a massive for a massive antenna array steering system would be something that I think is doable. Um, I think that the one we just demonstrated would not be able to work for such a number of antennas right now. I guess the main bottleneck that you would have to take into account right now is the data throughput between the USRPs and the computer that is processing the data. Right in this example, we had 4 channels for a 16 element antenna array, and that was already something challenging when it comes to signal processing for a two-dimensional antenna array steering. So I guess if you want to upscale it with many more antenna elements, you would have to somehow create a hierarchy between your processing systems in order to decentralize some of the processing. Right now, I can only think of the Argos system, which I believe demonstrated how you could connect some independent nodes in order to balance the computations between and upscale the system to a massive MIMO. But this kind of software management of the computation process was not implemented in our project.
Okay. Well, there was a question in the chat which I'd like to repeat here. How would the mathematics behind such a scaling look like? What are the challenges particularly? What do you see there?
I'm sorry. Can you just the math challenges according to scaling the system? What would it be? I'm sorry. I just had a cut during the.
Well, the questions from Bob, F4 GSW. What are the maths behind the array steering and massive FFT calculations?
Okay. In this example, we kept the math just using the computations and the IQ signals. We directly computed the phase shifts based on the IQ modulator, the information we got from the IQ modulator, as we have images of the same signal. But we could definitely use correlation for computation of the phase shift between our signals. In this case, we just chose this approach since the signals we used were pretty simple, and we were willing to completely make the phase shift computation independent from the sampling rate we were using in the signals. So that's just our choice, but a correlation would seem like a natural candidate as well for this. And with regards to the array steering, then the block only implement the usual array steering functions that you would equations that you would find in the literature. So the phase increments, the phase laws that you would use to steer a planar array are implemented in OO-Tignor radio blocks.
So maybe if I may, if you allow me to interrupt a little bit, I want to pick up on what Marcus said and what Clement is trying to answer. And I know that people have actually been doing massive MIMO transmissions for 5G test beds for a little bit, a while now, maybe 5 years, I guess. People from NYU and from Sweden, from Göteborg, they have been doing this, and they have been precisely doing this with the X310s. So saying that, I mean, they have connected massive arrays to lots of X310s. They're all synchronized with octoclocks and things like that. But saying this, I would like to ask Clement a question. So I would like to know if Clement thinks that is it in this setting where you want to do a massive array kind of beam steering thing, would it be interesting to separate your phase synchronization in a sort of a hierarchical level where you can put some part of it into the FPGA by synchronizing the antennas between themselves, and then another part outside on the computer doing the synchronization, the macro synchronization between the chunks of antennas?
Thank you, Leonardo. Yes, that would definitely be an interesting thing to explore. You're right to mention it. We did in this project. We did not exploit the available resources of the FPGA in order to increase our performances, but that would definitely be I guess the first place to start if we wanted to take that project further. So thank you for mentioning it. The FPGA would be a good start. Right now, I don't know if I would try to separate different steps of the phase calibration between the FPGA and the processor, but that would definitely be a lead to follow.
Right, and since you're using GNU Radio, there are already things that can be used for that. So that could be a good idea. So the things, right? There are ways to implement very easily GNU Radio onto the FPGA. So I think this could be something that maybe you guys can look on for the next part. And I think there's lots of inspiration from the people who have been done messing MIMO for the moment. Connecting to what Marcus was talking about the light, about seeing radio as light or something like that. I think that's one thing that has been happening a lot right now is I'm sorry, I'm hearing some feedback on my audio here. So okay, so I think it would be to go to higher frequencies. People are doing things with millimeter wave, and those are starting to behave a little bit more like light, right? So you have line of sight restrictions. Even the range is very limited. So this is maybe something that looks a lot like what Marcus is trying to say before. And speaking about that, so Clement, what are the limits of the system? What is the maximum speed that you can track with a beam steering, and what is the range? And I'm not at all an expert on this, but I think that ballistics go way over Mach 1. So is it feasible to actually track a missile that is going at Mach 3, Mach 4, or something higher than that?
Yes, you're right. That's a very interesting question. Thank you a lot for bringing that up. I would say, so we've presented some beam steering applications, and as we both mentioned, we are working with ballistic projectiles. So yeah, to answer your first questions, yeah, they can definitely fly much faster than Mach 1. I believe we've fired projectiles at Mach 3 with our proving ground a few years ago. and that with our capabilities we could go up to speeds even higher than that. So would antenna array steering be able to follow this kind of projectiles? That I would say definitely yes. During this PhD, we presented an application where we performed passive tracking of a projectile in which a transmitter was embedded. And that's the application that I mentioned in the presentation. And we were, I believe, maybe something like 120 meters away from the projectile trajectory. So even with speeds this high, in the end, the angular speed that would be seen by the antenna array is definitely something that electronic base steering, electronic beam steering is going to be able to keep up with. So we had absolutely no problem with this part, and we even carried out simulations in GNU radio, where instead of a signal that was truly received by the USRPs, we received signals that were phase shifted according to the angular variation that would be seen by the array for a projectile if the projectile flew at a speed of Mach 6. And even at that speed, we were able to follow the projectile accurately. So I believe the bottleneck of the technology is not going to be in that direction, especially since we showed the use case where the angular speed would be maximum seen by the array, since we are perpendicular to the trajectory. But here we showed also measurements for a two-dimension beam steering. So in this case, you could also think of putting the array behind the cannon and following the projectile if it has a ballistic trajectory. So in this case, the angular speed that you would see would be even lower. So that's not going to be an issue.
Yeah, however, maybe the Doppler spread is going to be higher, right? Because then you'll have the full speed against you.
Yeah.
So is that going to be a problem trying to track to the Doppler spread?
Yeah, the Doppler spread is definitely going to be a bigger concern. That's actually the specialty of my former colleague, Manuel Mija Penado, who presented in this conference 2 years ago. So we are investigating this field also in our team, and I believe Hervé would be able to answer some questions on this work I was not part of.
Okay. Well, I will stop taking.
It's not going to be an issue.
Yeah, however, maybe the Doppler spread is going to be higher, right? Because then you'll have the full speed against you.
Yeah.
So is that going to be a problem trying to track to the Doppler spread?
Yeah, the Doppler spread is definitely going to be a bigger concern. That's actually the specialty of my former colleague, Manuel Mija Penado, who presented in this conference 2 years ago. So we are investigating this field also in our team, and I believe Hervé would be able to answer some questions on this work I was not part of.
Okay. Well, I will stop taking.
It's not going to be an issue.
Yeah, however, maybe the Doppler spread is going to be higher, right? Because then you'll have the full speed against you.
Yeah.
So is that going to be a problem trying to track to the Doppler spread?
Yeah, the Doppler spread is definitely going to be a bigger concern. That's actually the specialty of my former colleague, Manuel Mija Penado, who presented in this conference 2 years ago. So we are investigating this field also in our team, and I believe Hervé would be able to answer some questions on this work I was not part of.
Okay. Well, I will stop taking.
It's not going to be an issue.
Yeah. However, maybe the Doppler spread is going to be higher, right? Because then you'll have the full speed against you.
Yeah.
So is that going to be a problem trying to track to the Doppler spread?
Yeah, the Doppler spread is definitely going to be a bigger concern. That's actually the specialty of my former colleague, Manuel Mija Penado, who presented in this conference 2 years ago. So we are investigating this field also in our team, and I believe Hervé would be able to answer some questions on this work I was not part of.
Okay. Well, I will stop taking.
It's not going to be an issue.
Yeah. However, maybe the Doppler spread is going to be higher, right? Because then you'll have the full speed against you.
Yeah.
So is that going to be a problem trying to track to the Doppler spread?
Yeah, the Doppler spread is definitely going to be a bigger concern. That's actually the specialty of my former colleague, Manuel Mija Penado, who presented in this conference 2 years ago. So we are investigating this field also in our team, and I believe Hervé would be able to answer some questions on this work I was not part of.
Okay. Well, I will stop taking.
It's not going to be an issue.
Yeah. However, maybe the Doppler spread is going to be higher, right? Because then you'll have the full speed against you.
Yeah.
So is that going to be a problem trying to track to the Doppler spread?
Yeah, the Doppler spread is definitely going to be a bigger concern. That's actually the specialty of my former
ways to control stuff.
Colleague, Manuel Mija Penado, who presented in this conference 2 years ago. So we are investigating this field also in our team, and I believe Hervé would be able to answer some questions on this work I was not part of.
Okay. Well, I will stop taking.
It's not going to be an issue.
Yeah. However, maybe the Doppler spread is going to be higher, right? Because then you'll have the full speed against you.
Yeah.
So is that going to be a problem trying to track to the Doppler spread?
Yeah, the Doppler spread is definitely going to be a bigger concern. That's actually the specialty of my former colleague, Manuel Mija Penado, who presented in this conference 2 years ago. So we are investigating this field also in our team, and I believe Hervé would be able to answer some questions on this work I was not part of.
Okay. Well, I will stop taking.
It's not going to be an issue.
Yeah. However, maybe the Doppler spread is going to be higher, right? Because then you'll have the full speed against you.
Yeah.
So is that going to be a problem trying to track to the Doppler spread?
Yeah, the Doppler spread is definitely going to be a bigger concern. That's actually the specialty of my former colleague, Manuel Mija Penado, who presented in this conference 2 years ago. So we are investigating this field also in our team, and I believe Hervé would be able to answer some questions on this work I was not part of.
Okay. Well, I will stop taking.
It's not going to be an issue.
Yeah, however, maybe the Doppler spread is going to be higher, right? Because then you'll have the full speed against you.
Yeah.
So is that going to be a
Yeah.
problem trying to track to the Doppler spread?
Yeah, the Doppler spread is definitely going to be a bigger concern. That's actually the specialty of my former colleague, Manuel Mija Penado, who presented in this conference 2 years ago. So we are investigating this field also in our team, and I believe Hervé would be able to answer some questions on this work I was not part of.
Okay. Well, I will stop taking.
It's not going to be an issue.
Yeah, however, maybe the Doppler spread is going to be higher, right? Because then you'll have the full speed against you.
Yeah.
So is that going to be a
Yeah.
problem trying to track to the Doppler spread?
Yeah, the Doppler spread is definitely going to be a bigger concern. That's actually the specialty of my former colleague, Manuel Mija Penado, who presented in this conference 2 years ago. So we are investigating this field also in our team, and I believe Hervé would be able to answer some questions on this work I was not part of.
Okay. Well, I will stop taking.
It's not going to be an issue.
Yeah, however, maybe the Doppler spread is going to be higher, right? Because then you'll have the full speed against you.
Yeah.
So is that going to be a
Yeah.
problem trying to track to the Doppler spread?
Yeah, the Doppler spread is definitely going to be a bigger concern. That's actually the specialty of my former colleague, Manuel Mija Penado, who presented in this conference 2 years ago. So we are investigating this field also in our team, and I believe Hervé would be able to answer some questions on this work I was not part of.
Okay. Well, I will stop taking.
It's not going to be an issue.
Yeah, however, maybe the Doppler spread is going to be higher, right? Because then you'll have the full speed against you.
Yeah.
So is that going to be a
Yeah.
problem trying to track to the Doppler spread?
Yeah, the Doppler spread is definitely going to be a bigger concern. That's actually the specialty of my former colleague, Manuel Mija Penado, who presented in this conference 2 years ago. So we are investigating this field also in our team, and I believe Hervé would be able to answer some questions on this work I was not part of.
Okay. Well, I will stop taking.
It's not going to be an issue.
Yeah, however, maybe the Doppler spread is going to be higher, right? Because then you'll have the full speed against you.
Yeah.
So is that going to be a
Yeah.
problem trying to track to the Doppler spread?
Yeah, the Doppler.
Very soon, Henning, you're going to be here around tomorrow anyway. And Clément, you've been here before. So hope to see you again very, very soon. Okay, thank you very much.
Thank you. Bye.
Goodbye.